Now, sure, we already know pH. We know that pH is just going to be the log of H plus, negative log of H plus. Or is it? Or is it something more complicated? Notice how we had to kind of just stagger through that, and that's probably where you're at. If you haven't looked at pH in a while, you probably had that kind of a process in your mind. Yeah, I know what pH is. Oh yeah, I forgot about the negative sign. Oh, you mean it's almost equal to? What's all this other nonsense? Well, remember, what we're talking about in reality, whenever we're talking about solutions and how things are interacting, what we're really considering is the activity of that atom. And now, normally we think of activity as being concentration, and the two are very similar. Activity is going to be the effective concentration once it starts interacting with other things that are present. Now, just to remind us of what the solution's looking like on the micro scale, if we have pure water, we're just going to have lots of little boomerangs like this. So actually I started drawing ahead of the story a little bit on the far right. So this is what things look like when it's just pure water. If I put in one solute molecule, there's not going to be a whole lot of an effect from that. Now suppose that there's a second solute present, and I should probably be putting counter ions in there too. Well, by and large, it's going to be just interacting with water because there aren't very many of them and there's tons of water molecules. But what happens is we start getting more of these ions present? Well, these are going to start repelling, but more importantly, these two are going to start attracting. And they're going to be able to bind together and help pull more things into solution that may have been solids on the bottom, or that may have been associated ion pairs, or whatever. Basically, by putting our positive and negative charges into the solution, we're making it more likely to get some more to dissolve. At least whenever we're talking about ions, we are. Now, there's a bit more of a nuanced argument when we actually talk about activity coefficients and talk about activity, but I wanted us to kind of have that in mind. So what we really care about in solution is the activity of the H plus ion. And the way that we can calculate that is we take the negative log of this whole term here, which is the activity coefficient. In other words, we go to some table and look up what the effective value is, and that's going to modify the concentration of H plus. What we're going to see is that it's basically going to make it act like it's a smaller concentration than is present, meaning more of it can dissolve. Or Le Chatelier's principle can pull it more toward being dissociated from the associated acid, so the HA form. In other words, we're making an approximation. That's why we have to say it's roughly equal to the negative log of H plus. Now, if it's a very dilute solution, then our activity coefficient should be roughly equal to 1. And that's one of the reasons that you'll often see that we try to work in fairly dilute solutions in analytical. Or at least, we tell ourselves, wow, the research I'm doing right now is very difficult because I'm working with tiny, tiny concentrations of things. Oh well, on the upside, at least I don't have to worry about activity coefficients. So that's the upside whenever you're doing these sort of things. Now, if you're doing high concentration things, then ignoring activity is only going to give you a crude approximation of what the real value will be. That said, people do that pretty frequently, especially outside of the hard analytical chemistry fields. So if you're working in a biological lab, people often don't focus on the activity coefficient quite so much. Now that said, if you've ever heard of the crowded cell model, where we're talking about how there's just tons of molecules inside of a cell packed into a very tiny volume, and there's going to be tons of complex interactions between all these molecules, activity coefficients start to turn incredibly important and actually incredibly complicated, because it's not just the activity coefficient of one substance, it's all of the different substances that could be present in the cell, whether they're polar or nonpolar. And things get very tricky very quickly. But remember that this is our definition for pH. Now I wanted to kind of pivot a little bit and talk about P whatever. We can use this exact expression to talk about the negative log of the activity coefficient of anything. And that will be roughly equal to the negative log of anything. And we do that all the time because often what we'll be doing is we'll be measuring, I don't know, how much of a particular metal ion is dissolved. So we could have pCa, which would be the negative log of the activity coefficient for the calcium ion, which equals approximately negative log of Ca plus. Sorry, that should have been a square bracket. My hand squiggled a little. There we are. And so you'll see in the text that sometimes we'll be talking about the P of Ag. In other words, P of silver ion. That's just going to be our negative log of silver ion. It gets things into a very easy to talk about format, where instead of talking about very tiny concentrations, times 10 to the negative 10, instead we're talking about pCa of 10. And that's really what it's telling us. So remember, whenever you have a P value, small numbers mean big concentration. If you have big numbers, that means a small concentration, because we're taking the negative log of that. Also, if you need to undo that and work back to find the concentration of something, we can always take the negative log to the 10th power. So we just do 10 to the negative pH, and that'll give us our concentration of, well, since I wrote pH, I should be saying H, but of course it could be whatever for that. That's all there is to that.